Chapter 22 will be dealing with alpha carbon chemistries, and we'll be looking specifically at enols and enolates. There are several biochemical processes in the metabolic pathway that involve alpha carbon chemistry. Glycolysis is one of these processes that makes ATP, or adenosine triphosphate, which is needed for energy. We will use a retro-Aldol process to break down the components to form that ATP. And an Aldol reaction, as you'll see in this chapter, involves alpha carbon chemistry. For carbonyl compounds, Greek letters are often used to describe where the atoms are in relation to the carbonyl center. So if this is the carbonyl, the carbon immediately next to it is the alpha position. 2 carbons over is beta, and then it's gamma and delta. So we're going to be looking at chemistry that's occurring at the position that is alpha to the carbonyl. A carbonyl, when reacted with catalytic acid or base, can form an enol. You can see the alkene here is the ene part of it, and then we have the OH as the ol part of it, so that's an enol. Reacting a carbonyl with a strong base forms the enolate. So the ate ending tells us there is an ion here. So we have the enol, but it's in ion form because it's O- instead of OH. This is an enolate. And what we can do is react either of those with an electrophile to form. The enol and the enolate can act as a nucleophile and do a nucleophilic addition, where we can form a bond to X here at the alpha carbon. The mechanism for the tautomerization, or the forming of the enol or enolate, depends on whether it is acid catalyzed or base catalyzed. So in the top condition here, this is acid catalyzed. And our first step is a proton transfer. The carbonyl becomes protonated, and it is resonance stabilized. If I take those electrons and put them onto the oxygen, this is no longer positive, but the positive moves here. So this is resonance stabilized. I have this acidic proton and water present. Water can abstract that proton and form the double bond here. And there's the double bond. So this is the enol. So this will occur under acidic conditions. In basic conditions, the hydroxide or a base will grab this acidic proton. These electrons will come onto the carbon. The negative charge is here. This is also resonance stabilized. We can move these electrons into form the double bond, and those electrons go on top of the oxygen. Get O-, and this here, this is your enolate. And then protonation with water forms the enol. So you want to notice in both of these situations, these reactions are reversible. If you have a strong base present, the enolate can form. We have a proton transfer, and those electrons can go onto the carbon. And this is resonance stabilized. This is the enolate. These protons here are acidic protons. The pKa is around 20. Enolates are much more nucleophilic than the enol. And that's because it has a formal negative charge versus the enol just has the oxygen lone pairs to do the attacking. Once we form the enolate, it can undergo an oxygen attack where the negative charge from the oxygen attacks an electrophile, and we get the OE. We can also get a carbon attack where the nucleophilic carbon can attack the electrophile with its negative charge, forming a new bond to that electrophile. Alpha protons are the only ones on an aldehyde or a ketone that can be removed to form an enolate. We can't take the beta or the gamma protons. Those are not resonance stabilized. So we want to draw all possible enolates that could form from the following molecules. The first structure here has a carbonyl next to a set of rings. We have the CH3 group over here. There are no alpha protons here, so we don't have to worry about taking any of those. This is the only one that can be picked up. We're drawing the enolate, which means it has to have a negative charge. So my base, we'll grab this proton, and we have the carbon getting the negative charge. Negative charge there, and you can also draw the resonance structure of that with the O having the negative charge. For acetone and acetophenone, acetone has 2 alpha hydrogens, however they're equivalent because this is a symmetrical molecule. So this would be the enolate, which is in resonance with this one. Acetophenone, there again is no H here, so we just have to worry about this one getting abstracted. The pKa of this alpha proton in acetone is around 19. For acetophenone is around 18. In a reaction with acetaldehyde, the pKa of the alpha proton is around 16.7. This right here, because it's acetaldehyde, is not an alpha proton. That's just an aldehyde proton. So the only one that we're looking at is this one right here. That can be abstracted by the base. And we get this enolate. You can draw the resonance form of that. Ethoxide can be a base that's used to abstract a proton. And when comparing the pKa's, we have 16.7 versus 15.9. In this case, the equilibrium is going to favor the acetaldehyde. If we use H- as our base, we can see that reaction happening there. So this is favored in the equilibrium. So if you want the carbonyl to react irreversibly, we want to use a strong base. One such strong base is lithium diisopropylamide. Or LDA. This is going to function to remove that proton, and we get the enolate formation. So you can see here the equilibrium is very greatly favored here. So if you want to use an enolate in your reaction, we want to use a strong base such as LDA to get it to react. If a proton is alpha to 2 different carbonyl groups or sandwiched in between them, its acidity is going to be increased. The pKa of this proton is around 9, whereas this one is 16.7 for acetaldehyde. In this case, it is okay to use the ethoxide It is okay to use ethoxide to form the enolate. pKa of ethanol is 15.9 versus 9. This side of the equilibrium is favored. We can do an alpha halogenation of enols and enolates. This carbonyl, when reacted with catalytic acid, can do a proton transfer. So we form the enol, and you can draw the resonance structure of that if you like. The water that was produced after the proton transfer can grab this acidic proton to form the enol. Once we have the enol, the lone pair from the oxygen can come down to reform that double bond, and these electrons can attack one of these bromines. Once the enol is formed, the electrons from the oxygen can come down to reform the double bond, which makes 5 bonds here. So these electron pair are going to do a nucleophilic attack on the bromine. The new bond will form to the alpha carbon. And we can just abstract that proton. So that is one way to brominate at the alpha position. In this case, we had a symmetric ketone, so it didn't matter which side it went to. If you have an asymmetric ketone, you get 2 products. When the bromine goes to the more substituted side, this is the major product. This is the minor product. And that is due to a more stable or more substituted enol. When doing an alpha halogenation followed by addition of a weak base, this is one way to get an alpha beta conjugated ketone. So alpha, this is beta. Now we form a double bond that's in conjugation with the carbonyl. The Hell-Volhard-Zelinsky reaction can brominate the alpha carbon of a carboxylic acid. So this works with the carboxylic acid, and it's the position that is alpha. So at 90% yield, we will brominate at the alpha position to the carbonyl. This requires Br2 and PBr3. Adding PBr3 to a carboxylic acid will change this OH, or the carboxylic acid, to bromine. This is an acid halide. In the process of that, this will form the acid halide enol. We react it with Br2, which will brominate alpha. Similar to as we saw in the last slide, the OH electrons can come down, and then those can attack the Br. To brominate here, we add water, which will hydrolyze the acid halide back to the carboxylic acid. We can also do alpha halogenation under basic conditions. Previously we saw it under acidic conditions. You had catalytic acid plus Br2. Here we're doing it under basic conditions. The product is the same. If you do it where there's multiple types of alpha protons, this is very messy. So halogenation is best under acidic conditions. Basic conditions is okay, but it's not preferred. If you have a methyl ketone, we can convert these to carboxylic acids using excess halogen and hydroxide. This is the haloform reaction. So in this reaction, we get the bromination of the methyl ketone. We add excess of that. This will happen 3 times. And with that OH minus present, that can attack here. This is now a fantastic leaving group. So these electrons can come back and reform the double bond. To get the carboxylic acid plus CBr3 minus. When the CBr3 becomes protonated, this is called a bromoform, which is where the haloform reaction comes from. So this reaction works with Cl2, Br2, and I2. And these work best when there's no other alpha protons present. In the next part of chapter 22, we're going to be looking at reactions that are called Aldol reactions. These typically involve aldehydes, which is where the ald part of it comes from. And in the process, we're going to make a beta hydroxyaldehyde. So the product that we're going to make involves the original aldehyde, and we get addition of a second molecule of the aldehyde, and there's an alpha beta position here. So this is a beta hydroxy carbonyl or a beta hydroxyaldehyde. And these are in equilibrium with each other. So the way that this reaction works is in typical chapter 22 fashion. There's going to be chemistry happening at the alpha position. So there's a hydrogen here. The pKa of that hydrogen is around 20. Sodium hydroxide is strong enough to pick up that hydrogen. So this will grab the proton, and it leaves the negative charge on that carbon, and these are in equilibrium with each other. And there's a negative charge here. We have a second molecule of the aldehyde floating around. That's going to be our electrophile. This is now acting as our nucleophile. So this nucleophile is free to attack this carbonyl electrophile, and those electrons will go up there to form that tetrahedral intermediate. So H here. So that's the original aldehyde. This is the new bond that was formed. I'm going to draw the second molecule in green here. This was the carbon that was attacked. There was a carbon attached to that carbon, and oxygen here. Those electrons got moved up, making a negative charge here. So this is your tetrahedral intermediate. This is the enolate. And we have water in solution. We just get a proton transfer. So the original aldehyde, new bond, second molecule of aldehyde, and the proton. So there is our beta hydroxycarbonyl. So when this is treated with hydroxide or an alkoxide, the equilibrium forms significant amounts of the enolate here, which is present, and that's going to feature both the aldehyde and alcohol groups in the product. So the OH is on the beta carbon. You can work out the mechanism for each of these if you want, but I will give you the shortcut as to how to figure out what the product is. Alright, so one method is to draw the original aldehyde. And then from the alpha position, which is here, you draw a new bond, and then you're going to draw the second molecule of the aldehyde. This is this carbon here, which is this carbon. That becomes an OH, and then it's everything else that came along. So 1, 2, 3. So you would get that. That's one way to draw it. So this happens in 75% yield versus the 25 in the equilibrium here. The other way that you can draw it is both going to be the same product. It's just a different way of thinking about it. So you have your original aldehyde. Then you know the reaction is going to happen at the alpha position. So I have 1, 2, 3 carbons. So 1, 2, 3. I'm just going to draw that flipped down here. And then we're going to hold hands or draw a new bond to the new aldehyde. That would be the OH here. And then 1, 2, 3. So there's two ways of drawing it. Both are correct. And these are both the beta hydroxy aldehyde. They're just drawn a little bit differently in the rotation process. The aldol reaction is in equilibrium, and it usually favors the products. Occasionally it doesn't favor products. In this case with cyclohexanone, 80% is preferred over the aldol product. And that looks like this. So you can also do them with ketones, the aldol reaction. So there's my original ketone or carbonyl. I have a new bond. This is the carbon that is right here. There's an OH there. And then I also have the rest of the cyclohexane molecule. This is 20%. Once we've made our beta hydroxy carbonyl, if we add acid or base in the presence of heat, this is going to get eliminated. This double bond forms here plus water. This is an alpha beta unsaturated carbonyl. The reaction that we saw here, these are aldol reactions. If you heat up the reaction in the presence of acid or base, this is an aldol condensation. So the aldol condensation gives off water, and we end up with the alpha beta unsaturated ketone. So the shortcut for drawing these, we can use the same two methods. Draw the original aldehyde. At the beta position, you draw your second molecule. This is our asterisk carbon. We have, this one was where the alcohol is. This is the carbon next to it, and then I have an alpha group here. So in this case, we won't be able to make the alpha beta unsaturated because there's no protons to get eliminated here. The elimination of water can be promoted under acidic or basic conditions, which we've already seen. Elimination or the double bond is going to occur between alpha and beta. So the double bond is here. So this hydrogen and water leave together. And then you add acid. We'll do the same thing. So under basic conditions, the base can grab the proton, and then OH can act as a leaving group. Typically OH is a bad leaving group, but if you're doing it in sodium hydroxide, that's an okay leaving group. And under acidic conditions, the OH will get protonated, and then that will leave as water with the elimination of this alpha proton here. So in this reaction with acid aldehyde, we draw the original aldehyde, and you can think of flipping this carbonyl here, chopping that oxygen off, and just laying that whole thing right there. So this would be if you took this and turned it on its side and then plopped it on here. So you take the oxygen off and put it where the alpha carbon is. So you can get this product with the stereochemistry here, or you can get this stereochemistry. There's two products possible. The aldol condensation is usually favored, so it's very difficult to isolate just the aldol product without getting it eliminated. So it's hard to see this beta hydroxy carbonyl. That usually goes right on to the alkene. So if you had cyclohexanone, we saw earlier that this is 20% yield, but if you do the reaction at 100 degrees, you'll get 90% of the aldol condensation product. At low temperatures, the condensation is less favored, so if at 10 degrees you get 20%, and even that is not great. But if you wanted to isolate the alcohol, you could do it at cooler temperatures. Okay, so if we were going to predict this product here, let's pretend this carbon is not here just to simplify things. Go through the mechanism if that helps, or you can use the trick here. Redraw your aldehyde, and then you can take the whole molecule, remove the oxygen here. So you're going to chop that off and just put it next to where the alpha carbonyl is, which is here. And then you have the CH2 and then the cyclopentane ring. So that would be one of the products. This is probably the major one due to sterics. Versus that one right there.